thank you for letting me present my works that I am doing in my thesis. We use the word multi-scale finite element method for incompressible flow. And I work with Gregor Valère at Polytechnique and Pascal Innes at CE. And with the help of Frédéric Edge and Pierre Jolivet for the implementation. Now, first, I will present you the context and motivation of this work. Then I will say a few words about the multi-scale finite element method. Then I will develop this method for the Stokes problem. And I will focus on the well-posedness of the local problem that poses lots of problems. And I think I will skip the error estimate because we have no time. And I will conclude with some numerical results. First, for the context and motivations, we have to note that multi-scale problems are ubiquitous. We can say, for example, composite materials, noise, which is composed of different layers with different properties, or the airflow in a density, where the building constitutes the total obstacle. But in my case, I am interested by solving the flow in the nuclear reactor cause. That is a multi-scale medium with many obstacles. We can cite, for example, the grid, the road, or the spacer. And what we want to do, and first, to model this problem, we consider a perforated domain in 2D or in 3D. That is consists of a domain omega, perforated by a set of perforations B epsilon. And epsilon is the characteristic size of the perforations. And what we want to do in this domain, the goal of this work is solve the Navier-Stokes equation in this domain. But as you may know, this equation is difficult to solve. So we will focus first on the Stokes problem in red in this slide. So on the classical Stokes problem, we different equal to 0. And we consider the critical conditions around the obstacle and what you want on the domain of omega, if it's a clear domain boundary condition. And I say U epsilon and P epsilon to recall that we solve this velocity and pressure in a perforated domain. And what this works, first, the motivation of this works is that if we discretize this problem with the classical finite element, let's say Kosoravia, we know that the error is given by this by 3 of this. And if we do some numerical analysis in the perforated domain, we know that the term that we call B epsilon is of order 1 over epsilon, the size of the obstacle. And since epsilon is small, this reckoning that the mesh size H is much smaller than epsilon. And it is generally too expensive numerically. And so several numerical multi-scale approach has been implemented in literatures. We can cite the H domain or LZ. And in this work, we are focused on the multi-scale finite element method. So what is this method? This method is to solve a global problem defined on the Planck mesh as this, using a Galerkin approximation classically. But in this case, the basis functions are no longer classical Lagrange polynomial, let's say P1, P2, or P1, or Pn, but it will be suitably chosen local basis function that solve a local equation in coarse mesh, in a fine mesh defined in each coarse element. And this basis function is defined in the physical computing, in our case with the Stokes equations, and it will take into account the obstacle or over local heterogeneity. As we see, the coarse mesh don't take into account the obstacle. And one important thing is that this basis function do not depend on the load F and the boundary condition G. So it is very relevant in the parametric, in metric context. That is to say, when we want to solve the same equations, but with different boundary conditions, and to extend. And this the multi-scale algorithm is like this. We begin with perforated domain like this, and we partition this domain in set of a coarse element that we call coarse mesh like this. And now for each coarse mesh, we can do it in parallel because each coarse element is independent each from others. We partition the element into a fine mesh like this, and we construct the multi-scale basis functions. And this construction can be done in parallel too, thanks to Pierre Jolivet. And then we compute the matrix locally on the fine mesh. And then we assume the global matrix and solve the cost problem on the cost mesh, on the global mesh. And we solve the problem. And this is called the boundary phase. It is a cheap computation because we have only a few elements. And after we can reconstruct the solution on the fine mesh. And how to find the multi-scale space? I give a generic approach like this. How to find the solution? So if we have a generic variational formulation like 4, like this, the idea is to decompose the velocity as UH plus U0, with UH belong to space of the resonance space, and U0 belongs to V0 and the space of the Anderson path, and that means. And then if we inject this formulation in type like this, and if we choose U0 and VH, that is to say, if we choose the resonance space and the unresonant path orthogonal with respect to A, we can forget the resonance space, and the equation 4 it's simplified as 6. And this problem is easy to solve if there is a solution. And then I will apply this technique for the Stokes problem. I begin for the classical variational formulation of the Stokes problem like this, with the classical finite element classical space. That is to say, we are looking the velocity in the space h1 0 of omega epsilon, and the pressure in L2 0 of omega epsilon. That is to use the value to ensure the uniqueness of the solutions. And then I will begin first. First, to build the multi-scale approximation, we begin from the initial space that we call the DH extended, because it extends the classical post-radial space. In this space, we consider the velocity in H1 in each element, but we control the jump of the velocity against polynomial of order n on the face. That is to say, it's like post-radial but extended. And we call the space, the velocity and pressure space extended like XH extended. And now the goal is to decompose this finite element space in an unresolved space XH0 of infinite dimension and a resolved space XH of finite dimension that will be our multi-scale space. So for the unresolved space, it is an arbitrary choice. We define our space like this, Vx0 and for the velocity and then mh0 for the pressure. So for the velocity, we take the velocity in Vh extended, but now we consider that the moment against the face is equal to 0, the moment of order n against the face, and the moment of order n minus 1 on the element equal to 0. And for the pressure, we consider the pressure on L2, but now we control the moment of the pressure in the element with polynomial of order. And the polynomial W, P, and bar P, I will call this the wave in the future. And then to find the result space, I will find the orthogonal of the space of XH0 according to the uniform CH. And by doing this, I find that I find a characterization of the result space. This is to say for the pressure is pressure in a polynomial of order n that is discontinuous. And the basis of pH, our multi-scale space, is defined by basis function that is defined in the space and basis function that is defined in the element. And I will say the variational formulation for this. So I have a variational formulation for the basis function. First, for the basis function associated to spaces, this basis function solves a Stokes type problem. But now we have a divergence that is polynomial, and we have some boundary conditions that is defined with Lagrange multipliers. And which is the type of basis function associated to element of the course mesh. We have resolved the problem with a polynomial source term in divergence polynomial, and with one algorithm defined by Lagrange multipliers. And we have to keep in mind that the divergence polynomial and the algorithm defined by Lagrange multipliers, because this will cause some problems to show the well-coordinates of the discrete problem. And I will do this. And then we compute the local basis functions. And I use function for this, and we have some basis functions like this. For example, we have basis functions defined elements or basis functions defined in the space. And we have to note that we have no explicit formulation of these basis functions. We have only the numerical values. But we can say a remark about this. We can say that, for example, on triangle, if we have no obstacle, we can say that P1 plus the polynomial of order n plus 1 is including VH. And then after having the local basis function, we can assemble the problem on the coarse mesh using a classical benefit formulation of the stocks. And this is and we can solve this with a direct solver because it's a coarse problem with only a few elements. And we have shown also the uniqueness of the discrete solution with our basis function. And then after obtaining the coarse solution, we can reconstruct the solution in the fine scale on the fine scale mesh, using a linear combination of our solution with the whole basis function. Now, I will focus on the well-posedness of the discrete local problem. That is the main part of my thesis. And I will recall that the discrete local problem, the local problem is defined by this. So to solve the local problem, I have said that the local problem have a polynomial divergence and Lagrange multipliers. So in each element, we cannot solve the local problem using classical finite element methods, let's say P2 given for stocks, or Creuser elements. So this has been a big problem. So the idea was to use Montanera. That is to say, the objective was to find a non-conforming finite element space with the same degree of freedom that our multi-scale finite multi-scale space. That is to say, the set of degree of freedom is given like this. It's given by the moment of the velocity against polynomial of order n of the phase, and moment of the velocity on element against polynomial of order n minus 1. And so, what we have done in 2D, we have found this finite element in the literature. It was a finite element developed by Gunnar Matisse and Lutz Pelitzer in 2005. And this finite element space is n plus 1 plus a subspace of Pn plus 2. And in free form, what we have done, in free form, we have the case n equal to 1 was already implemented. It was called element P2 Pn2. But we have implemented with Frederick H the case n equal to 2. And it is called the element P3 Pn2. And this finite element is a substat for the Stokes equation, so you can use it by loading discretely. But now, in 3D, such a finite element space does not exist. So during my thesis, I developed two family of finite element space, another 2 and another 3. Is defined as the same principle. That is to say, is Pn plus 1 plus a subspace of Pn plus 2, and the subspace is defined like this for the order 2 and order 3. And we have implemented this in free form with Frederick. And it is called element P2 PNC 3D and element P3 PNC 3D. And it is a pair of finite element that is encrypted for Stokes equations. And we have also an article in equations, notably with Pierre Jolivet, in which we present this finite element in a pre-continuing strategy for solving this efficiently. And then I think I will skip this part, but one thing I want to say is that, yes, one thing is that we have an error estimate too for the multi-scale approximation. And the error estimate is in H1, it's H power n, like classical finite element. But I will focus on numerical result. So I have done first in a small case in Python. It's a channel flow in perforated domain in 2D. So I have done in the left we have the multi-scale approximation on 64 element, and on the left there we have the reference solution, and on the right we have the multi-scale approximation. And first we see that the solution looks very similar, but on this we have only 64 course elements. And I have implemented several orders of the method, and we see that we have it's coherent with the theory. We have the good slope of convergence of this method. And now we have moved more complex cases. Now we have 128 by 128 perforations. And we take H is equal to epsilon over 25. It's about 10 power minus 4. And first we have computed the reference solution on the left and the multi-scale approximation on the right. And the reference solution has been computed on 1024 CPUs with state-of-the-art potential nodes, thanks to Pierre Jolivet. I think you explained it again. And on the right, we have the multi-scale approximations with only 1,000 course elements. And for this, it takes only a few minutes to compute, because it takes about 10 minutes per triangle to compute the basis functions. And then for the computation of the course problem, it's only a few minutes on one CPU. And visually, both solutions look very similar. And we are beginning to have some results in 3D exam. And I have not yet put the perforation in 3D, but I have just put the Taylor green with just to check the implementations. And we see that we have the good approximation with only a few course elements. I say it is 3,000 elements of this. And now we can move the ideas to move on bigger cases in 3D, because we have implemented more efficient solver with Pierre to solve the local problem. And then to conclude, we can say that we have an error estimate for the multi-scale approximations, and we have developed a new family of non-conforming finite elements in 3D. And we have implemented 3 new finite elements in Python. It's available from the version 4.5, I think. And we have implemented this method to solve the Stokes and Austin equations, but I have not considered those in this presentation. And so in future, the goal is to continue to study numerically this method for the Austin equations, notably with the Petrov Galecki formulations. And the goal is to investigate also the generalized multi-scale finite element method to solve Navier-Stokes equation, and maybe do some a posteriori estimate. And it's a reference, and thank you for your attention. If you have some questions.
You seem to have used only periodic cells.
Yeah.
And so, of course, I can see that. Why? Because you have only one domain and you have different conditions, but you could have done it for any geometry with maybe 60 different domains. Did you try that?
The domain, what you call the triangles?
The cells.
The cells, no, I haven't tried that. I guess,
Because
but I don't use the
you are
periodicity
in
of the cells.
competition with homogenization when you use only one cell. So either you need to compare with homogenization
Yes, because
or do a more difficult test.
yes, because I have done the periodic case because for the homogenization and for the error estimate in the periodic setting.
Yeah, okay.
But for the multi-scale, we don't need this.
Yeah.
And it was developed originally for a non-periodic domain. Because I think if you use some periodic domain, we have more efficient method than multi-scale.
Your error estimates that you have square root.
Yes. Yes, I have enough focus on this. Yes, yes. I can explain more the error estimate, but I have no time on this. So the error estimate depend on epsilon and h power n. It is not like a classical finite element method because finite element method you have h n plus 1. So we lose 1 over of h. But if we do some numerical analysis, we know that this term is off under epsilon 2. So you know that the error is basically given like this. H n plus square root of epsilon plus the square root of epsilon over h. And this is yes, this is the classical. So this term is negligible because it's overestimated due to quantum layers. And this last term is classical in multi-scale theory. It is called the resonance error. And it becomes problematic when epsilon becomes very small. So it is dominant, and we find the mesh is not efficient. But there is some, if you know some theory about this, there is some method to remove this error with some oversampling or something like this. But it's a classical term in multi-scale approach.
Another question?
No more. So from the web,